continue with what we were discussing in the last class. That's to say, essentially the computational methodology in order to have a fast computation to obtain the alphas to determine the speech coding parameters. So in that we are going to specifically discuss about the two fast approaches. One is what is due to Cholesky, and this is about the square root method in order to determine the the coefficients in a fast way. And then after Cholesky's decomposition, we are going to talk about a recursive approach by Durbin. So, and Durbin's recursive approach, and this second one, that is Durbin's recursive approach, is going to tell us about the solution of Toeplitz matrix. So essentially, since we have to do Toeplitz matrix inversion, so that is being done in a very efficient and iterative way. So at first we start with Cholesky's decomposition, which we had already introduced. The very basic concept of it was introduced. See, basically we start there with the set of P equations given by summation alpha k phi n I k, and that was equal to phi n I 0, and k was summed up for k is equal to 1 to p, where p is the order of prediction. So we essentially have p such equations from which we have to solve. So we have the equivalent matrix equation written as the phi matrix multiplied by the alpha vector, and that was equal to psi vector, where psi vector was the row vector that is consisting of not the row, but rather the column vector, which is consisting of this phi n's. So this is how we represent it in terms of matrix. And as per Cholesky's decomposition, what we are going to do is that this matrix phi we are going to express as a product V D V transpose, where V is the lower triangular matrix whose diagonal elements are all ones, and D is a diagonal matrix, okay, having all 0 elements outside the diagonals. So now this definition of phi, if we put forward, okay, so in this case V is lower triangular with all diagonal elements 1. So now what we do is that let us solve for the ijth element of this expression, okay. So from this matrix expression we obtain the ijth term, and the ijth term can be expressed like this, that we can write phi n ij. This can be expressed from this matrix equation as k is equal to 1 to j, and then we can write v I k dk v j k, and in this case the index, the summation index j, that goes from 1 to I minus 1, okay, where I is which one? I is the first index that we are putting for the correlation term, okay. So the summation k is from 1 to j, right, and this expression, actually what we can do is that this summation k is equal to 1 to j, we can just write it as a sum of two terms. One is that this summation expression only, what we can write as k is equal to 1 to, let's say if we write up to j minus 1, leaving the jth term, right, jth term in the summation process. Then we can write k is equal to 1 to j minus 1 v I k dk v j k as usual, plus we are going to have the jth term. And what is the jth term? For k is equal to j, we can write plus Vij, right, and then this is going to be Dj, and then this is going to be Vjj, Vjj. And what is Vjj? Vjj is nothing but the diagonal element of the V matrix, which by our choice of the matrix decomposition, we have made Vjj as equal to 1. Okay. So which means to say that this additional extra term becomes Vij into Dj only, right. So we can write it as Vij Dj. This can be expressed as phi of n I comma j minus summation k is equal to 1 to j minus 1 Vik dk Vjk, okay, for j lying between 1 to I minus 1, as usual what we had done, okay. And then for the diagonal elements, okay, we can write down from this expression itself that when we put this as the phi n I, so for the diagonal elements, we are going to write it as phi n I, okay, and that is going to be that it will be, this expression is going to be the summation k is equal to 1 to I minus 1. If I write the minus term, first is that, okay, phi n is equal to summation k is equal to 1 to I Vik dk Vik, just this expression, just this expression, and I am substituting I in place of j, right. So having that, Vik remains same, dk remains same, Vjk becomes Vik, and the index of summation becomes k is equal to 1 to I. Or equivalently from this expression, what we can write, if we take this one, right, if we take this one, then it becomes Vii into di, Vii is 1. So then we can write as di, the left hand side becomes di, and di becomes equal to phi n I minus this becomes k is equal to 1 to I minus 1. So just see, we can write first that di becomes equal to phi n I minus summation k is equal to 1 to, what is the summation limit? I minus 1, and then what it becomes, just j gets replaced by I, so it becomes Vik square, right. So it becomes Vik square into dk, okay. And then this equation actually gives us something very useful. Actually, if we write down the matrix expression, if we just break up the matrix expression, okay, what we had written means the original matrix expression phi expressed in terms of this, okay, and noting that all the diagonal elements of this V matrix, they are equal to 1. If we multiply, in that case we will be observing that the phi 1 1 term, okay, that becomes equal to d1, okay. So noting that condition, if we put that phi 1 1 becomes equal to d1, in that case using d1 we will be able to compute the terms beyond d1. That means to say that for d2, d3, etc., we can make use of this. So what we can do is that we can compute this for I greater than or equal to 2 with the condition that d1 becomes equal to phi n 1 1. This d1 is equal to phi n 1 1 is taken as the boundary condition, and using this boundary condition it will be possible for us to compute this equation, okay, for I is equal to 2, 3, etc. onwards, right. So see, I mean, when we put d is equal to 2, what happens? Just see, then d2 becomes equal to phi n 2 2. Now phi n 2 2 is something that we can compute, because we are going to compute the correlation values anyway. So phi n 2 2 will be determined from our speech samples, and this minus k is equal to 1 2, whenever we are putting I is equal to 2, in that case it is only one term that results. So with k is equal to 1, so using that we have only d1 term only will be required, and d1 is already known to us. D1 is nothing but phi n 1 1, right. So when d2 is known accordingly, then we already know d1 and d2, and using the knowledge of d1 and d2 we can now compute d3, right, because to compute d3 the summation will be k is equal to 1 2, now it will be 2. So there will be two terms, one is d1 term, one is the other is d2 term. We know both d1 and d2 terms, so we will be able to compute d3. So this is the way we can iteratively find out the values of the diagonal elements. So this way it will permit us to know the diagonal elements, okay, and once the diagonal elements are known, okay, you can make use of this equation, okay, in order to determine the elements of the V matrix, okay. So if V matrix is known, the diagonal elements are known, then what you are knowing is that in this basic matrix equation, okay, you are knowing V, D, and V transpose is obviously known, and by knowing this V and D, it will really permit us to do an efficient matrix inversion for this phi, because from this expression what are we supposed to do? We are supposed to solve for alpha. So which means to say that alpha will be nothing but phi inverse into psi, right. So to compute phi inverse will be expressed in terms of this V D V transpose, okay, and once the elements of this V matrix, D matrix, these are known, okay, this matrix inversion can be efficiently solved, right. So I just want to give you an exercise, okay, which you can try out, and that is to say that you consider an example with p is equal to 4. So consider, so this is an exercise for you. So consider an example with p is equal to 4. So fourth order predictor we mean. So fourth order predictor means what is the size of our matrix? Matrix is going to be of 4 by 4 size, okay. So with p is equal to 4, and instead of writing the matrix elements as phi n ij, so matrix elements phi ij, you just write it in a simpler way, and matrix elements phi n ij, simply write it as, just drop this n because this n is implied, write it as phi ij, okay, and then you can express the elements of V matrix and D matrix in terms of phi ij's. So you will get a feel of the decomposition. Right. So I mean we know that decomposition is not something which will be very difficult for us, okay. Now let us go back to our original equation, okay. Phi alpha is equal to psi. We are talking of this original equation, and in this original equation now, in place of phi we are going to substitute this V D V transpose. So if we do that, then what are we going to get? We are going to get V D V transpose alpha, and that is equal to psi, right. So we can write it is write this expression as we can write it as Vy, V times Y matrix, and that is equal to the psi. Okay. In this case, what we are doing is that we are writing this d V transpose alpha, this we are writing as the Y matrix. So, which means to say that we can write V transpose alpha is going to be nothing but D inverse into Y, right. So, ultimately what we have to do is to solve for this alpha, right. So, let us see that whether this writing this expression as V transpose alpha is equal to D inverse Y, okay, really helps us in getting any efficient solution or not. Okay. So, now let us just have a look at this equation. So, better that we number the equations. Okay. Let us say that we call this first basic equation we number as equation 1. Okay. Then this phi is equal to Vd V transpose, what we are doing after the decomposition, this we are writing as the equation number 2, and then let us number this one as equation 3, and then this we write as equation 4, and this one we will be calling as equation 5, this one as equation 6, right. So, now from equation 4, the matrix equation what we get, okay, this can be written again when we solve for the ijth element, okay, we should be able to write it this way. By the way, what is the nature of this Y matrix? Is it a matrix or is it a vector? What you feel? This is a vector, okay, because after all what happens is that this d V transpose that is a matrix and alpha is a vector, okay. So, ultimately it just makes into a p element vector. So, essentially what we want to do is to write down the ith element, and the ith element, this can be written from the equation 4 as. So, from equation 4, we will be obtaining that yi is equal to psi I minus summation j is equal to 1 to I minus 1 Vij Yj, okay, and I greater than I lying between p and 2. Now, here this equation we call as 7. Now, you know that how we have obtained it. We must have obtained it in a very similar way. We have obtained in a very similar way. Essentially, what you can write directly from equation 4 is that you could have written the equation 4's ith term as psi I could have been written as the summation j is equal to 1 to I, right, and then we would have written it as Vij Yj. This would have been the summation from j is equal to 1 to I, and like in the previous way we are just going to split this summation into two terms. One is j is equal to 1 to I minus 1 Vij Yj plus then the ii term. So, which will be Vii Yi, and this Vii Yi is nothing but Yi. So, that is what we are writing in equation 7, but just see writing like this really helps us. How? Because now Yi we are writing in terms of Yj, right, and if we do a recursion from I varying from 2 to p, okay, in this case what we are essentially doing is that, yes, I mean let us say that when we put I is equal to 2, in that case just j is equal to 1, only one term will be there in this summation. So, it will be V11. again you have an initial condition. Okay. So, leave aside this because this is how we are going to deduce it. So, from this we can write with an initial condition. This follows from the matrix expression itself. So, with what is the initial condition? The initial condition is that y1 is equal to psi 1, right. So, if y1 is known to you, in that case you just substitute y1 over here. So, j is equal to 1. So, when we have I is equal to 2, in that case y2, this can be determined in terms of y1 because we need psi 2. Psi 2 is determined because we are always measuring the correlation values. So, psi 2 is determined minus summation j is equal to 1, and this is going to be this vi1 term, okay, or rather to say we will be obtaining v21 when I is equal to 2, we will be obtaining v21 into y1, okay, and y1 in this expression will be known to you because of this initial condition. So, you get y2. So, writing like this essentially permits again another recursive relation to determine yi. So, this way we will be knowing the composition of this y matrix elements. Okay. So, having solved for y, equation 6 can be written as, so equation 6 is this much, okay. I mean this is our equation 6. So, y matrix elements are known, and in fact we can directly write down this as a recursion for alpha. So, what we obtain, so having solved for y, the equation 6 can be solved recursively, and okay, I mean I'll just go over to the next page to write down the recursive expression. So, solve recursively for what? For alpha, right. So, we are going to write the recursive relation as alpha I, and that is going to be yi upon di minus summation, it will be written as j is equal to I plus 1 to p v j alpha j, okay, and in this case I has to vary from 1 to p minus 1, okay, and the initial condition that we have to put here is, the initial condition will be alpha p equal to yp upon dp. Now, you see one beauty. Our initial condition so far used to be in terms of the first element, right, but in this case the initial condition is with respect to pth, that is to say the last element. So, just see, if we are putting alpha is if we are knowing alpha p only first, okay, then what we can do is that we can determine, I mean by putting the value of I to be equal to p minus 1, right, we can solve for alpha p minus 1, and to solve for alpha p minus 1, okay, when you put I is equal to p minus 1, what results in the summation process? There is only one term with j is equal to p. So, it will be Vp into alpha p, and alpha p is known to you from the initial condition, right. So, having known alpha p, you will be able to solve for alpha p minus 1, okay, and having known alpha p and alpha p minus 1, you should be able to solve alpha p minus 2. So, in this case also it is a recursion, but only difference is that this is going to be a backward recursion, right. So, in this case, yes please, any questions? Vj, just a minute. Correct. This will be Vji. Yes, right. Thank you for pointing it out. Right. So now in this case, the index I proceeds backward from I is equal to p minus 1 to I is equal to 1. So now whatever we wanted to solve can be determined. So we can now solve for all the values of alpha. This is what we were looking for, right? So this is the first approach, that's to say the covariance approach. Okay, of course we discussed the covariance approach a little later, because first we had talked about the autocorrelation approach and then we had talked about the covariance approach. So the covariance approach, the alternative solution for alpha would be like this. So essentially what we did, okay, it may appear that as if to say that we have complicated a problem because the initial matrix equation looks so simple, phi alpha is equal to psi, okay, but it is the inversion which would have been the most troublesome part of it. But what we did, just to summarize, what we did was to break up the phi matrix, okay, into a decomposed product of V d V transpose. Okay, so we are just multiplying it with the triangular matrix, okay, lower triangular matrix and its transpose, and in between we are having the diagonal matrix. We solve for the elements of the V matrix and the D matrix, okay, and having obtained that, we are then ultimately through a recursion process we are going to determine the value of the alphas. So it can be numerically determined. So only thing is that there will be involvement of some multiplications in the process. So as a result of that, some computation will be involved, and assuming that P is generally not too high, okay, so that's why the order of the matrix will not be excessively large. We talk about P in general, okay, but what can be a typical practical value of P? P is equal to 3, P is equal to 4, like that, because we have seen, I mean, that it is experimentally also determined that beyond a predictor order higher than 4, it virtually contributes to nothing extra, okay, because the past samples are not really, I mean, those many past samples are really not needed. I mean, up to the first 3 or 4 past samples, that is good enough for the prediction process, right. So this is one very effective approach, and now we are going to talk about Darwin's recursive solution corresponding to the autocorrelation method, right. So we are going to talk about Darwin's recursion. As applicable to the autocorrelation equations. And in Darwin's approach, what we do is that we first begin with the basic equation. Now the basic equation is also a set of P equations as before, we know that. So what we know is that summation k is equal to 1 to P alpha k Rn mod of I minus k, okay, and that was equal to Rn I, and this is I varying from 1 to P, right. So we did not name the equations, so let's continue to number those equations. So yes, this one we called as 7, and then this one is only a derivation to obtain this, so that is not a problem. and initial condition we put as equation number 8, okay, for the earlier one, and then this alpha's recursion we call as the equation number 9, right. So this we call as equation number 9, and the initial condition of alpha we call as equation 10. So with this particular autocorrelation equation what we are writing becomes number 11, right. Now what we are going to do in the case of Darwin's recursive procedure is that we are not going into the actual derivation of the iteration, because after all there is a matrix inversion which will be needed, that you can very clearly understand, because basically what we are having on the left hand side is a matrix of this Rn elements, and because of this Rn mod of I minus k, it results in the Toeplitz matrix what we had already discussed in the last class, right. So essentially it is the inversion of the Toeplitz matrix, and if we follow the inversion steps, then there is a very beautiful iterative methodology that results, and what we can essentially write down is that the steps of iteration will be written in terms of the error terms, right, the prediction error, because after all what we are doing is that we are predicting the function, okay, using the past sample. So there is going to be a prediction error, and if we just take some initial prediction error, the initial prediction error is going to be that of R0, and then one can iteratively solve, okay, and get the solutions for the alphas ultimately, because ultimately we will be interested in solving for alphas in an efficient iterative way, okay. So what we do is that in these steps we will just make some simplified way of writing. We will be dropping this suffix n, right. So instead of writing it as Rni, we will be simply writing it as Ri, right. So what we do is that the recursive procedure we can write like this. So we write as E the error, and the initial estimate or the 0th estimate of the error. So we are going to write it as E, and on top we write a superscript keeping 0 within the parenthesis, okay. So 0 within the parenthesis means it is the initial condition. So E0 is written as R0, okay, that is the autocorrelation value, okay, 0 0. So which means to say that this is the power expression. So E0 is R0, and then Ki is a quantity which we will be defining iteratively. Essentially you will be obtaining the Ki like this. So Ki will be written as Ri minus summation j is equal to 1 to I minus 1, and then it will be alpha j time superscript I minus 1 r I minus j, okay. This is one equation. So this term we have to divide by E of I minus 1, okay, and this has to be done for I varying from 1 to p. So what we will do is that this we will call as equation number 12, and this we will call as equation number 13. So essentially what we are trying to do in equation number 13 is like this. 13 is going to be an iterative equation. You can see, let us see that what results when I is equal to 1. If you put I is equal to 1, then you have E0 over here, then you have alpha j 0, you have got R0 over here as the first term, okay, because the expression is j is equal to 1, okay, and then you will be able to obtain alpha 1. So, you just need an initial estimate of alpha. With the initial estimate of alpha, you will be able to obtain the value of ki, right. So, this ki, that will be used in order to determine the next set of quantities. Okay. In fact, what results is that the alpha I estimate, that becomes equal to ki. So, we can write down as equation 14, we write down alpha I of I. Do not worry, I will illustrate that with a very simple example of p is equal to 2. So, that means to say with just a second order predictor, okay, we will be illustrating this approach. So, this will be alpha I, ith estimate, that will be equal to ki. Okay. So, we can compute ki having known E0, we will be able to compute ki. Ri's are all known to us. So, all that we need to do is with an initial estimate of this alphas, okay, and we can solve for this ki, and this ki's will be the next estimate of the alpha. So, alpha I will be equal to ki, and then alpha j of I, okay, can be updated from alpha j I minus 1 minus ki alpha I minus j I minus 1, okay, superscript. So, which means to say that whatever I minus 1th estimate was there, with that one can have ith estimate. In this case, j varies from 1 to I minus 1. So, this will be called as equation number 14. This will be called as equation number 15, and then from here we can obtain EI as 1 minus ki square into E I minus 1, right. So, that becomes the next estimate of E, call it equation 16, and from the next estimate of E, it should be possible for us to go back again to the iteration. That is to say that if we now go over to equation 13, 14, equation 13 to 16, if we repeat, okay, for all the values of i's up to p, in that case we obtain that alpha j, the final estimate of this alpha will be alpha j for the corresponding to the pth iteration. So, all that we can say is that equations 13 to 16, these are solved recursively for I is equal to 1, 2, etc. up to p, okay, and this is the final solution. Okay. So, this we can just simply illustrate with a simple example of p is equal to 2, okay, a second order predictor. So, if we take a second order predictor, then from this equation, that is from equation number 11, what we have to write is simply in terms of a 2 by 2 matrix for this R, right, and then just a two element vector alpha 1 and alpha 2 will be for this alpha k, and here again we will be having R1 and R2, okay, from this. So, what we do is that for a predictor of order 2, so we just illustrate our algorithm with an example that p is equal to 2, and then our basic matrix equation can be written as R0, R0 and this is going to be R1 and this is R1. So, this is a Toeplitz matrix definitely, because the diagonal elements are all same, these are symmetric, and also the next diagonal, which is consisting of only one element, is R1. So, this is definitely a Toeplitz matrix, and then this is alpha 1 alpha 2, and then we have R1 R2, and the idea is to solve for this alpha 1 alpha 2. So, going by our iterative approach what we presented, okay. So, just have a look at the iterative approach and just verify that what I am writing is correct or not. So, you just keep in your notebook, you just keep these equations handy, that is to say equation number 12, 13, 14, 15, 16. So, equation 12 to 16 you just keep, okay. Let us call this as 17, okay. So, you just keep these equations with you and then follow how we illustrate this example. What is E0? E0 is nothing but the R0, right, and what is going to be K1 in this case? Just see, K1 means you have to apply equation number 13, okay. You have to apply equation number 13, and there you have to put k is equal to 1. Sorry, you have to put I is equal to 1, right. So, which means to say that K1 will be equal to what? It will be R1, okay, minus what? J is equal to 1 to 0. What does that mean? Don't do it. Don't do the summation. You don't have to compute this summation. So, it will be simply a R1, right, and this divided by E of 0. So, it will be R0 by R1 by E0, right, because this is for I is equal to 1. So, it is R1 divided by R0. So, R1 by R0, and having known that, now what is it that you are going to have? In fact, I mean, this is one beauty of the algorithm, maybe that I did not explicitly note and tell you this point while I was writing down the equation. You see, yes, of course, I was telling you that some initial estimate of alphas are needed. That is not needed, in fact. So, what you are doing is that you are only determining this K1, okay, and while you are computing K1, you will never be requiring this summation, this second summation what we have, okay. This summation term will be 0, okay, for this. So, you will always be getting your K1 expression in this manner, and with the K1 you can have an estimate of the alphas. So, having known K1, what is going to be the application of equation? So, what is equation 14 going to give us now? Tell me. K1 is known. So, alpha 1 1, right. So, alpha 1 1 is going to be equal to K1, right. So, we now obtain an estimate of this. So, this will be K1. K1 means the same. It is R1 upon R0, right. So, now what about the alpha j's? Because j varies. I mean, look at equation 15. Equation 15 says that j varies from 1 to I minus 1. So, in this case, what is our I? I is equal to 1. So, that means to say that there is no particular solution for this 15. That is what we can is meaningful, okay. So, we cannot obtain I is equal to a solution for j is equal to 2 in this case. So, which means to say that we have to satisfy with the alpha 1 estimate only, right, because equation 15 we cannot apply simply. So in that case, what we have to do is directly to go over to equation number 16 with I is equal to 1. So that means to say that we can now obtain E1, right? E1 in terms of E0, because if we put I is equal to 1, in that case it is E0. So E1 is equal to 1 minus K1 square into E0. So let us apply that. We know K1 is R1 by R0, and the other thing is that E0 also we know that it is R0. So just tell me that what is going to be E1. E1 is equal to R0 square minus R1 square by R0, correct, beautiful. R0 square minus R1 square upon R0, right. So this is our E1, and now what are we going to do in the next step? Put K is equal to 2, right. So now we have to solve for K2. So K2 is going to be, you can just verify after putting into the expression, because now with K is equal to 2, just have a look at 13, okay, at equation number 13. Now we are going to solve for K is equal to, for I is equal to 2. So K2 will be equal to R2 minus the summation will be J is equal to 1 to what is I? I is equal to 2. So J is equal to 1 only. So only one term will be remaining corresponding to J is equal to 1. And what is that? Alpha 1, alpha 1 1, and alpha 1 1 we know already. Alpha 1 1 we require. I is equal to 2, okay, and J is equal to 1. So alpha 1 1 R1. This upon, in this case with I is equal to 2, it is E1 we just now computed, right. So what we have to do in this case is that we will be obtaining from this K2 is equal to R2 R0 minus R square 1, this upon R square 0 minus R square 1. This is the expression for K2, right. And then having known K2, we will be in a position to have alpha 2 2. Alpha 2 2 will be nothing but K2. So then this will be the same, R2 R0 minus R square 1 divided by R square 0 minus R square 1. This will be alpha 2, right. And then we also obtain, now we will be in a position to apply that other equation which we could not apply in the last iteration, that is to say equation number 15. Now we can apply equation number 15 for J is equal to 1 to, for J is equal to 1 we will be able to apply. So which means to say that alpha 1 with I is equal to 2. So alpha 1's second estimate now we can obtain. So alpha 1's second estimate, that becomes equal to R1 R0 minus R1 R2 divided by R0 square minus R1 square, okay. And then what we have obtained? We have obtained alpha 2 second iteration, alpha 1 second iteration. Anything more we require? Do we have to go through another iteration? No need, because we have to stop the iteration for I is equal to 2 in this case, because it is only up to P, that is what we have to go, right, and we are having P is equal to 2. So P is equal to 2, so whatever are the alpha i's pth estimate, that becomes the final estimate of the alphas. So, in this case we can say that alpha 1 is equal to alpha 1 superscript 2 and alpha 2 is equal to alpha 2 superscript 2. See, the only point to be noted here is that, look, alpha 1, for that it is really the second estimate. Now, for alpha 2, although the superscript we are writing as 2, but alpha 2 is what we have obtained for the first time. So, what happens is that for a general pth order estimate, okay, when we have the terms going from alpha 1 to alpha p, the first iteration will only yield alpha 1. The second iteration will yield alpha 1 and alpha 2. The third iteration will yield alpha 1, alpha 2, alpha 3. So, what happens is that alpha 1 is getting modified, is getting updated. Alpha 2 is also getting updated, but to a lesser extent, because alpha 2 we did not have initially. And the last term, that is to say the alpha p, that will get estimated only once, but that is after a long iterative process. So, that is why the estimate that we are having already for the alpha p's are close to the accurate estimate, right. So, this is one effective computational approach that one can take in order to determine the coefficients, this predictor coefficients alphas, okay, and this is what we were requiring. Now, these two methodologies are very popular, and in fact the two approaches that I discussed today, that means to say the Cholesky's decomposition pertaining to the pertaining to the covariance method, and Durbin's recursion, what we described just now, pertaining to the autocorrelation method, okay, both are very effective techniques, and we can summarize that there are two basic steps what you must have observed in these solutions. There are two basic steps. One is to obtain the elements of the correlation matrix, okay. So, we have to obtain the phi matrix elements or the R matrix elements by computing the correlation. That is the first step, and the second step is the iterative solution of these P equations. Now, these two are disjointed steps in the sense that you first need the formation of this correlation elements, and then you have to apply the iterative solution technique. You cannot have the second one without the solution of the first one. Now, this approach, these two disjointed approaches can be integrated if we go in for what is called as a lattice method of solution. So, in that case it is basically a filtering technique, okay, that will be a lattice structured digital filter realization through which we will be able to integrate these two steps, okay, combinedly, okay, and we can obtain the solution for the alphas very efficiently. So, this lattice structure of filters and the lattice formulation, that we will be taking up in the next lecture, okay. Thank you.